Radar is used to calculate the range and bearing of a target and thereafter use the information to determine speed, course and risk of collision. This information helps with navigating your vessel with regard to collision avoidance. Radar is used by vessel traffic management systems in controlling coastal traffic and is used extensively in pilotage. Radar is used for fixing the ship's position using terrestrial objects such as coastlines and beacons. Radar can be used to determine state of the weather, to an extent. Radar can be used for parallel indexing. Radar can be integrated with other shipboard equipment such as ICDIS to cross-reference data. All ships of 300 gross tonnage and above and all passenger vessels shall be fitted with a 9 GHz radar and an electronic plotting aid. All ships of 500 GRT and above shall be fitted with an automatic tracking aid to plot the range and bearing of other targets. Radio detection and ranging is used to detect objects and their position relative to your current location. It works by sending out a radio signal. When the signal hits an object, it gets reflected back to the radar, which can then calculate a rough estimate of the object. There are 4 basic elements in any functional radar: transmitter, antenna, receiver, and display. The radio frequency RF energy is transmitted from the transmitter via the antenna to and reflected from the reflecting object. A small portion of the reflected energy returns to the radar set receiver via the antenna. This returned energy is displayed on the screen and called an echo, just as it is in sound terminology. The antenna is used to transmit the radio waves. Open-array radar scanners, shown on the right, deliver higher sensitivity, better target detection and improved target separation. The marine radar is classified under the X-band 10 GHz or S-band 3 GHz frequencies. The X-band, being of higher frequency, is used for a sharper image and better resolution, whereas the S-band is used especially when in rain or fog as well as for identification and tracking. It is actually a component of the radar, called the magnetron, that is classified by its transmitting frequency band. There are 2 main frequency bands in commercial radar: X-band 9000 MHz band, wavelength 3 cm, and S-band 3000 MHz band, wavelength 10 cm. Magnetron output power ranges from 1 kW for small radars to 60 kW for large radars. The working process of radar starts with an oscillator known as the magnetron, which is a fixed frequency. The magnetron takes electrical inputs from a power source through a modulator and produces an output of electromagnetic energy known as pulse. These pulses are sent to the scanner or the antennae through a metallic tube known as waveguide. From the scanner, these pulses are sent out to the atmosphere. The number of pulses sent out through the scanner per second is called the pulse repetition frequency. The pulses travel through the atmosphere at the speed of light and gets reflected back after striking any target on its way. The reflected echoes reach back the scanner and the receiver processes and amplifies it and shows on the display screen as a blip, which is identified as the detected target. The delay line stores the energy from the power source. The modulator switches the magnetron on and off and releases one direct current pulse from the delay line to the magnetron. When the radio waves hit objects, some of the waves are reflected back to and received by the antenna. The antenna acts as a receiver too. The TR cell blocks the receiver part of the waveguide during transmission and blocks the transmitter end during reception. The duplexer switches the antenna from transmitter to receiver mode and vice versa. The microwave integrated circuit or mixer mixes the received echoes with local oscillations. The IF amplifier amplifies the intermediate frequency signal output by the mixer. The received IF signal is an analog signal. This signal is converted to a digital signal in order to undergo various processing in the display unit. The A/D analog to digital converter converts analog signals to digital signals. The limiter protects the receiver circuits from damage in the event one ship's radar receives radio pulses from another ship's radar. When this occurs, the limiter attenuates them to protect the mixer. Pulse length is defined as the duration of a single transmitted radar pulse and is often quoted in microseconds (s), although pulses rather shorter than 1 s are sometimes given in nanoseconds. The pulse width determines the minimum range at which targets can be detected. This minimum range is approximately 1/2 the length of the wave burst. In the case of the 4.5 microsine pulse, the minimum range would be 675 meters. This is also equal to approximately 0.36 nautical mile. The interval between successive transmitted pulses has to at least allow the transmitted signal to travel out to the furthest target of interest and back again. This interval is called the pulse repetition frequency (PRF), that is the number of pulses transmitted in 1 second. For example, a value of 1500 pulses per second, 1500 Hz. This is equivalent to 1 pulse every 667 microseconds. A radar antenna is designed to focus the transmitted energy into a beam which is very narrow in the horizontal plane. The angle within which the energy is constrained is called the horizontal beam width. It must have a value of not more than 2.0 degrees if it is to comply with the international regulations which govern marine radar. The beam width of the radar results in echoes being extended in the azimuth direction, hence azimuth distortion. It is apparent that azimuth distortion will result in an enlargement of a target by approximately 1/2 beam width on either side, so total enlargement is equal to 1 beam width. Radar resolution is the ability of the radar to show two targets which are close to each other as separate targets on radar. There are two types of radar resolution: range resolution and bearing resolution. As the name suggests, better bearing resolution means radar can paint two near targets on same bearing as separate ones. Bearing resolution depends upon horizontal beam width of the radio wave. Same way, better range resolution means radar can paint two close targets, on different bearings, as separate ones. Range resolution depends upon pulse length.
Radar resolution is the ability of the radar to show two targets which are close to each other as separate targets on radar. There are two types of radar resolution: range resolution and bearing resolution. As the name suggests, better bearing resolution means radar can paint two near targets on same bearing as separate ones. Bearing resolution depends upon horizontal beam width of the radio wave. Same way, better range resolution means radar can paint two close targets, on different bearings, as separate ones. Range resolution depends upon pulse length.
We are going to be using radar bearings for position lines. Bearing resolution is a measure of the capability of the radar to display as separate targets the echoes received from two targets that are at the same range and close together. The principal factor affecting bearing resolution is horizontal beam width. The narrower the horizontal beam width, the better the bearing resolution. We are going to be using radar ranges for position lines. Range resolution is a measure of the capability of the radar to display as separate pips the echoes received from two targets that are on the same bearing and are close together. The main factor that affects range resolution is pulse length. A short pulse length gives better range resolution than a long pulse length. Generally, we should use a short pulse length on short ranges for better range resolution, and a long pulse length on long ranges for longer range detection. Vertical beam width is the angular width of the path taken by the radar pulse. Vertical beam width is between 20 to 25 degrees. The minimum detectable range depends on the height of the radar scanner. Doubling the output power of a typical radar raises the maximum detectable range by only 19%. In the reverse case, having the output power lowers the maximum detectable range by 16%. While you can increase the maximum detectable range by using a high output power radar, a more economical way to do it would be to mount the scanner as high as possible above the waterline and/or utilize a longer antenna to increase horizontal beam width. When the radar pulse passes through the atmosphere, it gradually diminishes in strength. This is called attenuation. When the radar pulse passes through the atmosphere, it breaks up. This is called diffraction. The orientation of the display unit should be such that the user is looking ahead, the lookout view is not obscured, and there is minimum ambient light on the display.